We have previously discussed how to determine whether a bond is polar or nonpolar, but what we need to talk about now is incorporating the concept of bond polarity and molecular geometry in order to determine whether a molecule itself is polar or nonpolar. Now, in order for a molecule to be nonpolar, its bond dipoles, which are the dipoles that exist between the two atoms, they must cancel each other out. What you need to keep in mind is that a bond dipole is a vector. And by a vector, I mean that the magnitude of that dipole is important, and also the direction of that dipole. So if you look at the diagrams below, you can notice HCl, it shows the dipole arrow right there. Okay. Notice that HCl is polar, and the reason why it's polar is because the bond dipole that exists, that vector right there, which is pointing to the right, it is not canceled out. If you look at BF3, which is right below it, you have a bond dipole facing upwards. You've got one going downwards to the left and one going downwards to the right. If you imagine this as a tug of war, if you've got going up and downwards at a diagonal, those bond dipoles actually cancel each other out, and therefore the molecule is nonpolar. CCl4, this tetrahedral in the center, is a little bit harder to see, but since you have a dipole face pulling upwards, you got one going down, three going downwards. Those actually also cancel each other out, and we'll actually look at a molecular model kit to see that one a little bit more clearly. But that one's also nonpolar. You can think of it as a tug of war. Imagine those green atoms, those chlorine atoms, are pulling on the central atom of carbon, and that carbon would not move. Now, if you look at NH3, you've got a vector, you've got three different vectors pointing towards your central atom, which is nitrogen. Now, notice you don't have anything pushing downwards on nitrogen. Therefore, the bond dipoles do not cancel each other out, and therefore the molecule is polar. And finally, if you notice, we have CH3Cl. Now, if you look at this one, you would think at first that it would be nonpolar like CCl4, but if you notice, while you have three hydrogens, you also have a chlorine. Now that chlorine is more electronegative, so it's going to be hogging electrons towards it. That's why the vector is pointing towards the chlorine atom, and therefore the bond dipoles do not cancel each other out. Now, if we're going to talk quantitatively about the polarity of molecules, the dipole moment of a nonpolar molecule, that is going to be 0, meaning that the vectors cancel each other out. So keep in mind there is a strong distinction between bonds being polar. In this case, all of these examples, all of the bonds are polar, and you can see that by the arrows. Do notice that there are not vectors, there are not bond dipoles between carbon and hydrogen, and the reason why is that the electronegativity difference between carbon and hydrogen is so small that we do not acknowledge it. So keep that one exception in mind, but for all the other ones, all these other bonds are polar. The polarity of the molecule, however, depends on vectors canceling each other out. We're now going to take all of these concepts that we've been talking about for the last couple of units, so the Vesper theory, which we just looked at, and then also orbitals, and we're going to consider them together by looking at the valence bond theory. Now that takes the concept of atomic orbitals in the Vesper model, and it explains why bonds exist between atoms. Now, what it specifically states is that the buildup of electron density, remember we had talked about the fact that the electrons of opposite atoms are attracted to the nuclei, and therefore you have a large electron density in between atoms, which is the covalent bond. What the valence bond theory states is that that results from the overlap of atomic orbitals. Now, it's not as simple as what I'm about to show you, and I'll explain in the next section, but this is a nice quick view. As you can see, the bond between the hydrogens, the covalent bond, that results from the overlapping of your 1s orbitals. For hydrogen and chlorine, that covalent bond exists due to the overlap of the 1s and the 3p, and same thing for the chlorines. Now, we're going to look at this in a little bit more detail because we have to talk about hybridization in just one second. But as a review, if you were wondering, well, how close do the hydrogen atoms get to each other, or how close do the hydrogen and chlorine atoms get together, keep in mind this graph, which is on the right-hand side that we'd already discussed. Remember that there are a number of electrostatic forces that are at work. You have the attractive forces of the nucleus and the electrons, but then also the fact that the nuclei of two different atoms repel each other, and that their electrons also repel each other. So if I'm starting at the top of this graph, remember, if your energy is above zero, that means you have repulsive forces. And so if your hydrogen atoms, or your hydrogen and chlorine atoms, or your chlorine atoms are too close together, they're going to repel, their nuclei are going to repel each other, until as you travel down you get to 0.74 angstroms. This is the ideal distance between the two nuclei, because you have balanced the repulsive forces of the nuclei and the electrons with the attractive forces between the nuclei and the other electron. As you continue to increase the distance between the atoms, between their nuclei, however, based on Coulomb's law, the attractive force decreases until you reach zero. So that's just a nice review incorporating new information that we've also looked at. Now, as I had stated before, unfortunately, when we're looking at bonding, it's not quite as simple as, oh, these two orbitals overlap and that's it. We have to create what are called hybrid orbitals in order for our Vesper model to line up with what is actually happening with the atomic orbitals. So I'm going to explain hybrid orbitals with an example. A lot of textbooks just explain hybrid orbitals and it's really confusing, but I'm going to explain the reasoning behind hybrid orbitals and why they exist. Even though this is not going to be tested on the AP, I want to make sure you guys understand it instead of just memorizing it, because that's what I did when I took AP Chem. Alright, so if I have BeF2, I'm going to be looking at beryllium. Now, the orbital diagram of beryllium is 1s2, 2s2, and I showed that orbital diagram right down there. Now, what you should notice is that beryllium needs to be sharing electrons with fluorine, but it doesn't have any unshared electrons. So what it's going to do is it's going to promote one of those 2s electrons into the 2p orbital. Alright, now you have a 2s and a 2p unpaired electrons, and those can be shared with fluorine. Now here's the issue. If beryllium shares a 2s and a 2p electron, the bonds between beryllium and fluorine, you would have two totally different looking bonds. But that's not the case. Those bonds are identical. And so as a result, there aren't actually 2s and 2p orbitals that are sharing the electrons with fluorine. Instead, you have a mix of those two orbitals. And that's represented with an sp orbital. So you take the 2s, the 2p orbitals, and you blend them together into an sp orbital. So notice I have two electrons in my sp orbital, and those are going to be shared with fluorine. And the reasoning behind it, again, is that the bonds are identical between each beryllium and fluorine, and therefore we have to blend the atomic orbital so you don't have two distinct bonds. So this is what that blending looks like, that hybridization looks like. You have an S and a P hybridized together, and the SP looks like this. Notice one lobe is very small, the other one is very large, and when they are shown together, you see this combination of the two large lobes. So that's what the SP hybridized orbital looks like. Notice if beryllium were in the center and fluorines were off to the side, that would be a linear molecular geometry, and that's actually what we see based on the Vesper model. So hybridization corresponds with our predictions based on the Vesper model, which is very convenient. Now the question you're probably asking is, well, every single time that I am representing the bonding that occurs between atoms in a molecule, do I have to show or explain why hybridization occurs? No, you do not. Instead, all you have to do is follow these three steps. I just wanted to make sure you understood where hybridization came from. So the first step is to draw the Lewis structure. So pause this video right now, please, and draw the Lewis structure for BF3. Now the next thing that you need to do is determine the electron pair geometry based on the Vesper model. Now, the electron pair geometry for this, there are three bonding pairs, there are no non-bonding pairs, and therefore the electron pair geometry is trigonal planar. Now we need to specify the hybrid orbitals needed to accommodate the electron pairs in this arrangement. Notice there are 3 electron domains, and therefore the hybridization for this is going to be Sp2. Notice S, there's 1 P and then you have 2 P, so Sp2. So if, for example, I have only 2 electron domains, then my hybridization would be Sp. If I had 4, it would be Sp3, a total of 4. Okay, so let's get a little bit more practice with this. So Sp2. This is actually what Sp2 looks like. Notice this works fantastically. You have 1 S, you have 2 Ps, and that creates the trigonal planar shape, molecular geometry that we had anticipated using the VSEPR model. Okay. This is your Sp3. Notice it creates that tetrahedral shape that we would anticipate if we had 4 electron domains. So you have 1 S orbital that's combining with 3 P orbitals. Next, we're going to talk about what happens when you have multiple bonds, because up until this point, the only thing we've been talking about without actually realizing it is sigma bonds. Now, sigma bonds are the electron density between 2 nuclei. They're just the covalent bond. So whenever you see a single covalent bond, you are talking about sigma bonds, that overlapping, that large, high electron density between atoms. That is your sigma bond. However, if you have more than just a single covalent bond, which we've already experienced, oh, and by the way, this is your sigma bond right here, that overlapping. If you have more than one single covalent bond, if you have a double or a triple covalent bond, then you're going to also have pi bonds involved. Now, pi bonds result from the overlap of orbitals above and below sigma bonds. They're a little harder to imagine, but here you go right here. Notice it's above and below. So what I'm going to do right now is I'm going to explain how pi bonds are formed, and then again, you're not going to need to be able to explain that in a problem. You're just going to need to be able to count how many pi bonds and sigma bonds, and I'll explain that as well. Alright, so here's the explanation for knowing how many pi bonds and how many sigma bonds you have. So I have this molecule right here. Notice I've already given you the answer. You have 1 sigma bond and you have 1 pi bond. But let's actually understand why that's the case. So let's look at carbon really quickly. Carbon has 1, 2, 3 electron domains. Therefore, the hybridization, the hybrid that's going to be formed from your 3 electron domains is Sp2. Okay? So let's see how that actually forms. Here's carbon right here. I've got 2 unshared electrons. Unfortunately, I actually want 3 unshared electrons, and therefore carbon is going to promote one of its 2s electrons into the 2p slot. Now, what you should notice is I only need 3 electrons. I have an Sp2 hybridized orbital. Therefore, I'm going to take the 2s, the 2px, and the 2py electrons, and I'm going to leave the 2pz electron because I don't need it. And so what happens, as you can see in the purple, this looks really crazy, but I promise you it's really not. The purple is your Sp2 hybridized orbital, so you have 3 of them. Now, remember, you had the 1 unhybridized p orbital, and that's represented in pink. That looks like a traditional p orbital. What happens is that the Sp2 orbitals will overlap right here, and that's represented with a sigma bond. The unhybridized p orbitals are actually going to, their electrons are going to overlap, and they're going to have an attraction. Keep in mind that pi bonds are not as strong as sigma bonds because you don't have that direct strong attraction that exists in a sigma bond. Instead, they're just slightly overlapping above and beyond where the sigma bond is. Also keep in mind, if you look at the very bottom diagram right here, this shows the hydrogens bonding to the carbon atoms. Notice the hydrogen, its orbital is just the 1s orbital, and so that's going to overlap with the Sp2 hybridized orbital and create those covalent bonds. there are two last things that I want to note. So when I'm asking you about how many pi bonds or sigma bonds a molecule will have, no, you do not need to go through this entire thing to figure out what's going on with the hybridized orbitals and figuring out what p orbitals are unhybridized, which ones are hybridized. Instead, all you have to do is the following. If you have a single covalent bond, you have one sigma bond. If you have a double bond, what that means is that you have a sigma bond and one pi bond. If you have a triple bond, that means you have one sigma bond and two pi bonds. So you will always have one sigma bond, and then if you have more than just a single covalent bond, you will either have one or two pi bonds. The last thing I wanted to note, as you increase the number of bonds, so as you go from a single bond to a double bond to a triple bond, what we will notice as we move through this class is that double and triple bonded molecules are very inflexible. We'll look at that when we look at organic chemistry. Now the reason why, if you look at this, imagine those pink pi bonds didn't exist. That purple sigma bond, those atoms could twist around. Okay? Since that pink pi bond exists, however, it keeps them stuck so that they're unable to flip around and unable to rotate.